Welcome to another video. In this video, we're going to be testing different mixed integer linear programming solvers. And we'll be using this magical Beehive. So this is a logic puzzle from the Bent magazine. And maybe one of my favorite applications of binary variables is to implement logic puzzles in that sort of you can think of a binary variable as a yes, no, and it kind of opens up the door to a lot of interesting logic type puzzles. I've played around with making a Sudoku solver using linear programming and binary variables. So for this one, we'll consider this beehive shape, so kind of a hexagonal grid here. There's 19 cells in this kind of compound three-layered hexagon shape. And the goal is to fill all those spaces with the numbers 1 to 19 in the cells, such that all the rows and diagonals add up to 15. So sort of like a magic square, but a magic beehive here. And so kind of thinking of this as a row. And so there's 5 rows that are horizontal, but then there's also 5 diagonals that are running this way. And then there's also 5 diagonals that are running this way. Okay, and so that will give us sort of 15 different rows, some of them being horizontal, some diagonal, that all need to add up to the same total. So first step in implementing this is to give indexes to each of the locations in this puzzle. And so I've gone ahead and done that down here. I've essentially numbered each of the rows. So the horizontal rows I've numbered with the index I going from 1 to 5. The diagonals going this way, I've numbered with J also going from 1 to 5. And all the diagonals that are going this way, I've numbered with K going 1 through 5 as well. Okay. The thing to note about these indexes is I've got 3 indexes, but really it's only a 2D problem. And so I only really need 2 of these indexes to locate any position on here. The third index will tell me sort of that set of rows, which will be important for the row sums, but it's sort of dependent on the other 2. And so when we actually implement this, we don't want that sort of relationship between indexes, and so we'll actually only use 2 of the indexes. We'll use I and J. It turns out the K index we can compute as being J minus I plus 3, and you can kind of look over here and check that if I do J minus I and then add 3, I'll always get the K, which is the third index here. So I've sort of these locations in here are I, J, K, ordered triples there. Knowing that helps you out in a couple things because we know that K has to be between 1 through 5. If we kind of put those inequalities in with this formula here, we get that J has to be between I minus 2 and I plus 2. And so notice there's not every combination of I and J in here, but only the ones where J is between I minus 2 and I plus 2. And actually, you can also flip it around to know that I is between J minus 2 and J plus 2. So that sort of gives us our locations in here. The last thing that we're going to kind of do with our variables is kind of thinking about those variables is we'll have one more index that determines the value that we're going to fill into that hexagon. Okay, so we got the location, and then we'll have another index that has the value, and then we're going to create a binary variable that says if we put that number or that value in that hexagon, then that binary variable is true, otherwise it's false, or 1 and 0. Okay, and so essentially our binary variables are going to be X, I, J, V. I and J are the location. V is the value. And that value is going to be between 1 and 19 because we want to fill in each cell in the beehive with a value between 1 and 19 such that we're not repeating any values. So there's one value in each cell and each value is only used once. And then we need to also fulfill the row sums. And in this case, because there's sort of 5 rows in each direction, and the total sum of the entire beehive would be the sum of the numbers 1 through 19 is 190. If we take that 190 divided by 5, we know that each of the row sums needs to be 38. Okay, so that's sort of the setup for the logic puzzle. The constraints I've got below, but maybe before the constraints, we should talk about the objective. There is no objective. In many logic puzzles, this one included, the goal is just to find a solution that satisfies the constraints. Once we have a solution, there is really no objective value to it. So any solution is just as good as the other. And kind of thinking about this one, there's definitely some symmetry that there's going to be multiple solutions, and you could get some solutions by just sort of rotating the beehive, and that would still be a solution. So, but of those solutions, any of them is just as good as any other. So here are the constraints, is that only one value in each cell. And so if we add up across all the 19 values, there can only be one of them that's true. And we're going to get this constraint for each location in the beehive. Okay, I've left off the sort of conditions on the locations that I minus 2 is less than or equal to j is less than or equal to I plus 2. But those are sort of implied, and we'll have to implement them when we put them in code. But kind of for brevity, you can think about this as for each location. And then each value is only used once. We don't want multiple ones in our table or anything else. And so we have the sum over all the locations has to be 1 for each value. And so we're going to essentially check for the number 1 that it only shows up at 1 location. Same for the number 2 up through 19. And then these 3 are implementing the row sums. And so the value times the binary variable is going to essentially turn on and or off that value for that row. Okay, and we'll add together the values of the variables that are actually in use in that row. Okay, and so for each of the I rows, we'll sum over j and the values. And we want this combination of value times xijv to be equal to 38. Similar for the j rows. So those are sort of, the I rows are going along here and checking the sums. The j rows are going this direction and checking the sums. And then the last one, and maybe the more tricky one, is the k rows, which are going along here. And we're not using k as one of the actual indexes in our problem. And so there we have to use this relationship here, that k is equal to j minus I plus 3. And we'll have to rearrange that a little bit. But once we rearrange it, we can solve that I is equal to j minus k plus 3, and we can sub in j minus k plus 3 into here and have that for each k. Okay, and then we're going to sum over all the j's. Will sort of move us along that row for k. Okay, here's the model, just building the model. You can kind of see how we have to put in those constraints. So we got the indexes, and this is one thing I really like about the OMPR package, is it makes it really easy to give indexes as well as give sort of logical expressions for those indexes that sort of tell which of those indexes you want to actually include or not. And so here we're summing over I and j 1 through 5, but not all 5 by 5. That would give us 25 different terms in the sum, but we really only want the 19 that sort of fit into our beehive hexagon shape. And so we want to keep it that I minus 2 is less than or equal to j, and j is less than or equal to I plus 2. Notice you can't have compound inequalities. You just have to write them as 2 separate inequalities. Okay, and so that is the implementation of each of the 5 different constraint types. Only one value in each cell. Each value is used only once. The row sums along j, the row sums along I, and the row sums along k. I will point out we were implementing this as a binary. It is possible to implement this as an integer program where you just have indexes I and j, and then you let the actual variable take on the value that goes in the cell. Um, it's possible, but it's a lot trickier to implement that you only use each value once. It's possible. I played around with it. I got it working. I'll be honest, it was a lot slower. So uh, binary variables are pretty powerful, even when you're thinking about something that's integer in value. So really, each cell it gets filled with an integer, but sometimes having a binary indicator is actually easier. Okay. So the main point of this was to look at the different solvers for this. So here we've set up this problem. Now we can send it to the different solvers. First kind of line of attack would be to use the build or use the solvers that OMPR sort of plays nicely with through ROI. So OMPR allows you to sort of build the models. Once you hit solve, it's sending it down to ROI. ROI is sort of an interface that sends it out to different solver choices. And so far this semester, we've played around with GLPK as the underlying solver, as well as LP solve. But there's other choices. And so sort of when your problem's small enough, any of them will do just fine. Once once your problem gets big enough, there's some value to sort of testing out and seeing for my problem type, which of these solvers sort of works better than others. Okay. And it's not going to universally be true. So what I show you for this problem might not hold true on a different problem. This is sort of a very niche type of problem that has no objective. And so really, if you think about the branch and bound that's going on underneath the hood, there's not a lot of bounding going on because there is not an objective. And so, yeah, certain other algorithms might perform better than others on this problem, but that might be different for yours. So I encourage you to experiment a little bit, see which ones work best. So here are the solvers that you can use on this problem using the ROI plugins. And so if you take your model, turn it into an ROI model, which that's sort of provided by ompr.roi package. And then there's an available solvers function in ROI, and that will tell you all the solvers that are applicable and available for your problem. And so, I've sort of set it up so that it gives you the package as well as the repository. And so kind of looking through here, we see GLPK is one of them. We see LP solve. We see a couple others here. As far as repository, things that are on CRAN, CRAN, which is the Comprehensive R Archive Network, I believe is what it stands for, is where most R packages live. And so it's sort of the easiest place to get a package from. And so if it's on there, you can use the install.packages command to install it, or the tools menu and install packages, and that will just work fine. Some of these are hosted other places. All these ones that are the GitLab ROI GRP, that's the ROI group. And so they host some of the plugins for different solvers on their website. And then there's another one for CBC hosted on someone else's GitHub. I tried that one and I wasn't able to get it to install. And maybe if I'd played around with it a bit more, I could, but I kind of decided not to look too far into that. So today, for this video, I looked at two of them that we've seen before, LP solve and GLPK, as well as I thought Symphony was interesting. It's a open source project from CoinOR, which is a sort of operations research software project that's open source. And so I kind of decided I'd try that as an option. Here's sort of the solve times for this problem, and you can kind of get solve times by using the tick-tock package and the command tick and then tock. For LP solve, it solved it in just under 2.5 minutes, so not too bad. GLPK over 10 minutes, almost 10.5 minutes. Symphony, it took almost 2.5 hours. So I'll be honest, the couple times I had tested this, I'd started running and ran out of patience. Yesterday, I ran it and left my office and wondered this morning whether it would be done or not. And so was happy to see that it finished by the time I got back in the office this morning. So yeah, Symphony, at least for this problem, doesn't seem like the best choice, but for other problems, it might be very well suited to your problem. So feel free to give it a try. It might actually work well. So those are some options with internal solvers that are kind of built into R. You can also go with an external solver. And so ROI package has the ability to write your model to a file, and then that file is portable that you could use in an external solver, whether that's a commercial solver or an open source solver. And so we can take our Beehive model, convert it to an ROI model, and then ROI has ROI write. MPS is maybe one of the more common formats for a linear programming file. And there's a couple versions of it. We'll use MPS underscore fix there and create a Beehive MPS. You could then take this and use this in a couple of common commercial solvers would be Gurobi or Cplex. Those both are kind of common commercial solvers that are pretty powerful. An open source one, so CoinOR, who also produce Symphony or host Symphony. I'm not sure how much sort of interplay there is between the different CoinOR projects, has a solver called CBC. This uses branch cut, which is a variation on the branch and bound algorithm. And it's one that I've used in the past. And it seems to get pretty good speed up. So you can get CBC from the CoinOR web page. If you go to this site here, it will have a bunch of different options that of versions of CoinOR. And so find the one that matches your operating system. For Windows, this is the one that I found that works for me, though you might find a different one that works well. For Mac, this is sort of my best guess, but it might take a little bit of trial and error to get CBC working on a Mac. But the program comes in a zip file folder. Extract that zip folder, put your MPS file in the bin folder there, go to command prompt or terminal, navigate to that bin folder, and then you can run the command CBC, give it the MPS file that you want, then you solve, and then tell it to put the solution in a text file. Okay. Running it on my computer, it solved in about 85 seconds. And so faster than any of the internal solvers there. And I've found that it scales pretty well, and that couple past student projects, they've had ones where it was solving and taking several hours with some of the internal solvers, and then had kind of pretty drastic speed up when they brought it into CBC. Now, the output that you get from CBC is not the most user-friendly, and so Dr. Axfig has written sort of a parser to kind of take what you have from your CBC output and hopefully translate it into something that you can read and understand. And so kind of if you run this code chunk, that will create the function called CoinOR CBC solution parser. From there, you can give it the output of the CBC solution, and then give it some names of variables. And if you're using the OMPR package, the variable underscore keys stores the names of your variables. So you can kind of recall those there. And then if you run that, that will sort of give the solution with and put the names on it. So sort of looking through here, it's binary. And so anywhere there's a 1, that indicates that value is at that location. And so the 1, 1 location, which would be the top left corner of the Beehive grid, has a 9 in it. And then if we look in the 1, 2s, Let's see if I can pick out the ones. I don't see a 1 there, but I see a 1 here. So then the 1-2 position has a 14 and so forth. And I'd probably filter this to just show me where the ones are. But yeah, if you want to kind of look through the output here to sort of actually solve the Beehive, you can. If you want to avoid looking too closely at that and actually try to solve it yourself, you're welcome to play around trying to solve it without using the power of a solver. The long and the point, or the moral of this story, is mostly just experimentation. Whenever your problem gets large enough that it's slow enough, you're going to want to sort of experiment with what are the other options out there. The other thing I'd say is find a backup computer and be able to kind of run it where it's not interfering with you doing your other work. And so yeah, on campus here, I'll go check into the computer lab and run it on a computer that I don't have to worry about, and then check back an hour later and see if it's done. So that's just some tactics that you might need for your final project when your problems get big enough that they actually take a significant amount of time to solve. That's it for this video.